Gonna move that camera a little closer. There we go. It's pretty good. All right, back. Welcome back to class. So we were talking about first order systems. In the last class, we spent a very long example solving an RC problem. We're going to also solve now an RL problem. This one's going to be a little bit more complex of a circuit, but I'm going to step you through the solution process. You need to understand the solution process. Now we'll give you some steps to try to simplify this as this goes on, but this is complex, so. Okay, so now what I'm going to do here is yeah, I'm going to use another DC source, I guess. I suppose. I'll solve some RLC circuits in the future with a DC current source. Not this time around. Okay, so here, this is going to be an RL circuit, okay? We have VS. We'll set VS is equal to 10 volts. We have R1. We'll say that R1 is equal to 50 ohms. We have R2. We'll say that R2 is equal to 150 ohms. And then we'll say L, and we'll say L is equal to 5 henries. Okay? And then the question becomes, what is the long-term behavior of this system, and what is then the transient behavior of the system? In order to understand that, we have to establish an initial condition. I'm going to go ahead and draw a switch in here and say that the switch turns on at time 0. Our initial condition here is we're going to assume that the inductor IL is equal to 0 at t equals 0. Okay. Now there is something you will notice here. Whenever you solve a first order system, you are either solving for the voltage across the capacitor or the current through the inductor. Do not solve for anything else. Your life will be hell. It's awful. Horrible, horrible situation. Just don't do it. It's not worth your time. Okay? So here we are solving for the current through the inductor. And then the question is, I want you to graph IL as a function of time. Okay? All right, so that's our problem. We have our numbers. Now, just like last time, what we're going to start with, and here's the first step. Actually, I'm going to go ahead and give you the steps before we get started. Should make things a little simpler. Step number 1. Okay, this is identify all constituent and component equations. Again, constituent equations have to deal with the system as a whole. Component equations have to deal with the individual components of the relationship between the voltage and the current in those components. Okay? Second, what we're going to do is we're going to derive the system equation. And when we do so, we're doing it in terms of the forcing function, which here we have a voltage source, so it's going to be Vs, and the desired component. Component. And here that's either going to be Vc or IL. Do not solve for anything other than Vc or IL. That is step 2. Derive the system equation in terms of the forcing function and the desired component. Once you have that, Then we're going to kind of do a back-in solution. What we do is like what we did in the last problem. We identified here's what we know about VC, and then we stepped back through the problem to identify the components of it. You're going to write the equation for the final solution. Okay, and then basically what you do is step number 4, you solve the homogeneous problem, system equation, for S/tau. Okay, because tau is a function of S. S is a function of tau. Once you've done that, solve the full system equation for the particular solution. And then number 6, solve the final solution at some time to find the final variable. Okay? And then your last step is just to write it out. Okay? So those are the 7 steps to solving a first order system. To solve first order system. Okay. Kind of a big deal here. These are all points that every one of these steps, as long as you follow the steps, as long as you understand what you're doing through the steps, it is just an algorithm. It's just a process, okay? Mathematically, I described why we're doing each one of these. I'm going to kind of go through them a little bit quickly in this video. You can compare this to the previous video, but I would advise you spend some time thinking about what I'm doing and why I'm doing it as I go through these 7 steps. Okay, so we'll start with step number 1. FYI, you can go ahead and write these in your notes. I am going to erase these because you can pause this video, you can rewind it. I don't need this to be up on the board for very long. We'll do step number 1. Step number 1 is identifying the variables. Okay? So identifying the equations. So I have my KVL. In my KVL equation, I have 2 loops. Loop 1 says that VS is equal to VR1 plus VR2. This again must be true at all times t. And then it also says that VR2 is equal to VL. Also true for all times t. That cannot be violated. KCL. Okay? According to KCL, we have that IS is equal to IR1. IR1 is equal to IR2 plus IRL. In real life. And then the last one is IL plus IR2 is equal to IS. Okay? Those are our KCL equations. Both of these together comprise our constituent system equations. They have to be true in order for physics to be true. And the last one is our component equations, where we identify the relationship between voltage and current inside of the components. Here we have VR1 is equal to IR1 times R1. VR2 is equal to IR2, R2, both of those are Ohm's law. And then we have VL is equal to L DIL dt. Okay, so component equations, constitutive equations, good to go. We're going to derive our system equation now, which is step number 2. First equation I'm going to start with is one that has the forcing function in it. Here we do not have IS, we were given VS. So we're going to write this in terms of VS. VS is equal to VR1 plus VR2. It's the only equation we have on this board that has VS in it. This does not have VL in it. It doesn't have IL in it. We're trying to solve for IL. We are way far away. Okay, so I'm going to bring in this equation next. Vs is equal to VR1 plus VL. And then I'm going to take this equation and say, okay, where's another place where I have VL? Well, VL is right here. Vs is equal to VR1 plus L DIL dt. We now have this term in terms of IL, which is great. That's what we want. Okay, now we have to figure out VR1. Well, VR1, ooh, gross. Well, we have Vs is equal to VR1. Another equation for VR1 is, let's see, we've got this one up here, which would be going backwards. The only other one we have is that one. So IR1 R1 plus LDIL dt. Okay. Well, what equation do we have that has IR1? Well, we have this one, and then we have both this one and this one. Since we don't have the source current, that one's not going to be very helpful. But we do have this one right here. So Vs is equal to IR2 plus IL times R1 plus L DIL dt. Okay, well, we got the IL, we got the DIL, but now we have this weird IR2 equation. Now, because this is a system, all of these are interlinked. Because all of them are interlinked, what that means is we're dealing with, this has to be some function of IL. Okay, so we'll go ahead and figure that out. How can we figure that out? Well, where's another place where we have the equation for IR2? We have both of these. This would be taking a step backwards because we just used that equation. But we also have that one right there. So we have Vs is equal to, here, if we solve for IR2, it's equal to VR2 divided by R2. So VR2 over R2 plus IL times R1 plus L DIL dt. Well, VR2, we have this equation here, and we have that equation there, but these are the only two equations we have. This is the one we just used, so we're going to use this one instead. Vs is equal to VL over R2 plus IL times R1 plus L DIL dt. Well, we have this equation for VL, so we'll go ahead and bring that one out. Vs is equal to 1 over R2 times L DIL dt plus IL times R1 plus L DIL dt. Gross. Super gross. Disgusting. You disgust me, sir. But that is our equation. Not pretty, but we got it. Took a little bit of work. Okay, I'm not gonna... I was hoping that was candy. I don't know what that is. Don't you always hope that candy just randomly falls out of the sky? I mean, it can't hurt if it hits you, but it'd be fun otherwise. Okay, now I am going to go back and erase step 1. Again, you can review that if you really need to, but I only have a certain amount of whiteboard. Okay, so I will write my system equation here. I'm going to clean it up a little bit. This is number 2. And that is Vs is equal to, distribute the R1, so this one becomes R1L over R2 times DIL dt plus R1 DIL dt plus L DIL dt. Okay, that's kind of gross. We can combine these two. Dun, dun, dun. And then we get Vs is equal to R1L over R2 DIL. Whoa. This is IL. We're combining those two. My bad. Plus L DIL dt plus R1 IL. All right, so there's our system equation. Okay, Then I can go ahead and erase this. So that was step 2. We now have our system equation in terms of the forcing function, which here is Vs, because this is a voltage source, and in terms of IL, because that's the component we're looking for. It's not Vc, we don't have a capacitor here. So it's the only other one that we can solve for. All right, so now we've got step 2 down. Now step 3 is write the equation for the final solution. We know the final solution, I'll write a 3 here. We know that the final solution is going to be IL, as a function of time, is going to be equal to IL complementary, as a function of time, plus IL particular, as a function of time. Okay? Now here, if we go look at the complementary solution, it's gonna be the same thing. All first order complementary system solutions look exactly the same. It is ILC, as a function of time, is equal to A1 e to the negative t over tau. You could do A1 e to the st, that also works too. But I'm just short-circuiting this and gonna hang straight for the tau because tau makes sense. And I like tau. Tau be nice. The tau. ILP as a function of time. Here, if we look at the forcing function, the time function for the forcing function is a constant 10 volts. Because we know that this is a constant 10 volts, we're going to go ahead and just set this as a constant. Okay? Nice. All right, so that's fun. And now we've done step 3. Step 4, solve the homogeneous system equation for S or tau. And that's not S divided by tau, it's S or tau. So here we have step number 4. First step in step number 4 is to write the system equation as a homogeneous equation, which means we just replace the forcing function with 0. So this is R1 over R2L plus L times DILC dt plus R1 ILC. Okay, spoiler alert, this equation is going to get drug out like we found in the last one because it has to sum to 0. Da, da, da. So we have 0 is equal to R1L over R2 plus L times negative A1 over tau e to the negative t over tau plus R1 A1 e to the negative t over tau. Okay? All right, so that's fun. We can divide out A1 e to the negative t over tau, again, out of both of these, and what we end up with is 0 is equal to R1L over R2 plus L times negative 1 over tau plus R1. That's interesting. That's a fun word. Look at that, it's got the word R1 in it. Why not R2? It's got R2 right there. Let's blow up the Death Star. Okay, so we're going to want to solve for tau. So that's nice. What I'm going to do is I'm going to bring negative R1 over to this side is equal to R1L over R2 plus L times negative 1 over tau. I'm going to go ahead and multiply both sides by negative tau. So you end up with tau R1 is equal to R1L over R2 plus L. Divide both sides by R1, and the fun equation you get is tau is equal to L over R2 plus L over R1. That's delightful. That's step number 4. We've now solved for tau. Tau is a fun amalgamation of equations. And all of this is just geometry. Aside from up here where we actually had to take a derivative, but it's just, well, not geometry, it's algebra. It's math. So I'm going to go ahead and up her, right? Ching! Tau is equal to L over R2 plus L over R1. Okay. So now that we know that, I'm going to erase this because I'm out of board space. And then we're going to move on to step 5. All right, step 5, what we have is we're solving the full system equation for the particular solution. So here, we're solving for this. So I'll write 5 up on the board. And then what we have is we'll plug the particular solution back into the system equation. So here we have Vs is equal to R1L over R2 plus L DILP dt plus R1ILP. So we've got RILP at the end here. RILP. Nah, whatever. Okay, now I'm going to go ahead and just replace the particular solution with A2 because that's our guess for it. So we have Vs is equal to R1L over R2 plus L d over dt of A2 plus R1 times A2. Okay, well, we know the derivative of A2 is equal to 0, so that kind of goes away. And what we end up with is Vs is equal to R1 A2, which means that A2 is equal to Vs over R1. There are some interesting implications to this. We will discuss that in a little bit. So now I will go ahead and A2 is equal to Vs over R1. Nice. So that's step number 5. Now, for step number 6, we solve the final solution for some given time. We have to know what the system is doing at some time here. That is our initial conditions. So we go back up here, and at time equals 0, there's no current flowing through the inductor, so we can solve for that. So, step 6, choo-choo. We then go back and rewrite this equation from 3, but then we write out these terms. So here we've got ILT is equal to ILC plus ILP. Okay, so this is IL as a function of time is equal to A1E, which I'm going to give T over tau, plus A2. We know what A2 is, we know what tau is, and then we know the initial conditions, which is at T equals 0. We know what ILT is. So we plug those in. 0 is equal to A1E to the negative 0, because we're replacing T with 0, divided by this fun jazzmatazz, L over R2 plus L over R1 plus Vs over R1. Okay? Now, when you evaluate this at 0, it ends up just being 1. So this ends up being A1 plus Vs over R1. You divide that and you subtract that over, and you end up with A is equal to negative Vs over R1. And that is the solution to 6. So we can go ahead and write this over here. A1 is equal to negative Vs over R1. And then I'll erase this. The last step is we take the equation that we just wrote out, 3, and then we just write it in terms of all of our variables. So here we have IL as a function of time is equal to negative Vs over R1 times e to the negative t over L over R1 plus L over R2. You could clean this up if you really wanted to. I'm going to leave it like that, because why not? What's life without whimsy? Plus Vs divided by R1. Wow! There's a whole lot to unpack in here. Okay, so let's unpack it. Well, let's graph this before we get anything too wild. First of all, How long does it take before this reaches equilibrium? Well, let's calculate the value of tau. Tau is equal to L over R1 plus L over R2 is equal to L is 5, R1 is 50, R2 is 150. So 5 divided by 50 plus 5 divided by 150 is a fun number. 0.1333 repeating. Okay, so how long does it take to reach equilibrium? Steady state happens at 5 tau, which if I just multiply this number by 5, this is equal to 0.667 seconds. Okay, so about 2/3 of a second after that switch is flipped, this system has reached equilibrium. That's fun. Okay, so that's good to know. Now, what is the steady state behavior of this inductor? Now, we can look at it just without doing any math. We can just look at this and say, all right, at steady state, under a constant DC source, this is going to behave as if it is a short circuit, which means what you have is this resistor and then this resistor, which is in parallel with a short circuit, which basically means you only have that resistor. So at steady state, the current that's flowing through this inductor is going to be Vs divided by R1, which is why we see that. Okay? It's fun that we can mathematically verify what we can just look at. Nice. On the flip end of this, our initial condition happens at time equals 0, and it establishes a voltage value of 0, which means our total transient response has to capture going from 0 to eventually reaching Vs divided by R1. Okay? Going to this from this. Since we are given time t equals 0, what it means is our A1 value is going to be equal to, since our initial condition occurs at t equals 0, then what we end up with is A1 is equal to IL at 0 minus A2, okay? This has occurred in the last two equations, the last two problems that we've solved. If I have enough time on Thursday, I will go ahead and I'm going to solve one of these equations, and it is going to be ugly on purpose. So, you're welcome. Thanks, Mom, for making me a torturous human being. Well, we'll do that, and it won't be at time t equals 0. And I'll show you how to solve that. It's not fun. But this is just some very interesting things that we have because things are happening. Since our initial condition happens at t equals 0, this is going to be true, and we'll find this true every time. And so we started to identify some of the shortcuts. Okay? So I can go back in through here, and I can say, all right, well, one of the fun pieces of this really fun pieces of this is if I were to take this initial system equation and divide both sides by R1, what I would end up with is Vs over R1 is equal to L over R2 plus L over R1 DIL dt plus IL. And then you'll notice this is tau. Mind blown. So if you solve this system equation such that the variable itself is by itself, the coefficient in front of the derivative is tau. Okay? So that's fun. That would save us having to do that step. Particular solution, do you know what the steady state solution is? Here, if we would have been able to figure out the steady state solution, that would have taken care of that right there. Final solution at some time, had we known this, that would have taken care of that right there. We didn't have to do any derivatives to figure that one out. So there are shortcuts to solving first order systems, okay? Work back through it, and when we do some problems on Thursday, this should be a little bit more fun. All right, I'm hoping to be in class on Thursday. No guarantees. If I am in class on Thursday, expect a problem like this. Actually, I'm just gonna go ahead and record a problem like this and make you watch it, because you know what? Love. Nah. Yeah, I'm totally doing it. No, I'm not doing it. I'm kidding. We'll do it on Thursday. But we're going to go through all 7 of these steps, and I'm going to introduce it to you and why we can't do a very simple system like this, where this condition is true. This condition will be true no matter what on a first order system. It's really nice, very helpful. You'll also notice that this, which is over here, is our steady state solution. Whoa. Because this is our time varying solution. What? So, lots of fun things that happen that we didn't have to do a ton of math to figure out. We did them anyways. All right. Oh, let's graph this, because that's the last piece of this. Right, in order to graph this, I'm going to need to know some values. So here, A1 is equal to negative Vs over R1. That's going to be equal to negative 10 divided by 50 is equal to negative 0.2. A2 is equal to Vs over R1. It's equal to positive 0.2. That's equal to 0.667 seconds. Well, that's equal to 0.1333 seconds. That's for the time constant. Steady state will happen at approximately 0.667 seconds. Okay, so we can work with all of these numbers. I'm going to go ahead and erase this piece and draw my graphs over here. All right. Fun. So here we're going to graph IL as a function. Wow, that is a tiny graph. Let's not do tiny graph. I like big graph. IL is a function of t. Okay. Now we know that at time equals 0, IL is equal to 0, which means it's going to start here. We know at infinity, we're going to be approaching a value of 0.2. So I'm just going to go ahead and draw that on the graph. 0.2. This is, by the way, in terms of amps. So it's going to start at 0. It's going to approach 0.2. We'll call this point where it reaches steady state. And that's going to be at 0.667 seconds. Because, yes, FYI, this is in seconds. And then what we have is we just have a graph that looks like that. There we go. Okay, we're identifying the time where it reaches steady state. After this point, we can just assume that the value of the particular solution is the only value that we have for the system. Okay, so that's fun. All right, let's take some knowledge and now look at the rest of the system quickly while we have everything up on the board. Okay, so what I want to look at here is I want to be looking at IR2. Okay, now one of the constitutive equations that we had was that we knew IR2 plus IL had to be equal to IR1. Now IR1 actually is a changing function, which is itself very fun. But if we're looking at IR2, I guess we could look at VR2. I guess in order to do that, we need to step through to look at VL. Sorry, my bad. VL is equal to L DIL dt. Okay, so we take this, we take the derivative of this function, we go solve the derivative right here of this function in terms of time, multiply it by L. This is what we get. Okay, it's going to be something that looks like this, where here IL initially at t equals 0, we do the derivative of this, it's going to be super gross. It ends up being what? Negative 0.2 times 0.13333 e to the negative 0. That one goes away, so it ends up being 0.2, so it's what, about 0.026, I don't know, something like that. But we end up with that, and that's our initial current. 0.026, it represents the amount of voltage that is present in R2, ironically. Then that goes down to 0 here at 0.667 seconds. This can be assumed to be equal to 0. Okay. You'll also notice that because of our constitutive equations, this is the graph of VR, which means if we take this and divide by, well, this R2, we get IR2, and IR2 has this sort of relationship where eventually it reaches 0 at steady state time. Okay. Now, what we'll notice happens with IR1 is that IR1 ends up having a very similar equation to this. IR1 is equal to IR2 plus IL. If we sum these together, what ends up happening is you end up with a system that I believe, now this is 0.2, this is 0.02, which this is much larger than this one. It ends up looking something like this. Oh, my bad. Where it approaches 0.2, which is the steady state behavior. That's steady state, but it starts at that 0.026 something that this one starts at, 0.026, okay? So, it's kind of an interesting behavior. You still have some kind of curve that's going on there. IR1 is not constant. Now, if we were to take IR1 and multiply it by Vs, which IR1 is equal to Is, you get the power in the system, PS, which is slightly curved upward. It is not constant, which is what we saw in the last one. It is an exponential function that reaches your steady state value of 0.2 multiplied by, well, 0.2 squared multiplied by 50. Which I guess I can do that math real quick. 0.2 squared times 50, which is equal to it approaches a value of 4 watts. Sorry, 2 watts. I can't read numbers. Okay. So, fun times. At this point in the system, at t equals 0, all of the power in the system is being consumed by these, well, really, by these two systems. This forces it to have no voltage across here at, oh no, it forces it to have a voltage across here at some certain amount of time. This prevents it from having any current at t equals 0, which is why IL is 0 at that point. There's no current. That's what it was before. It stays at 0. This one has to handle all of the current, which is why it has a positive voltage. That voltage then decreases as the current continues to be diverged into this branch of the circuit, which is why IR2 decreases to 0. Okay? This one does decrease because what you're having is there is a decreased resistance to flow in the system. Because less current is being diverted to R2, what that means is there's less resistance to current flowing as time progresses. Because there's less resistance, you're going to see an increase in current on that component, which is also why you see an increase in power consumption in the system. All right. So this was a fun example. If I can't be here on Thursday, expect more lectures from me online. I don't want to do that to you because this kind of sucks in video format. Because you really can't ask questions. You do have a quiz that is over this type of material. You will be able to start on it as of today. To do this Friday, I might bump back the due date till next Tuesday. But do know that you've got another quiz due next Thursday. And then when you get back from break, test. So that sucks. All right. Hopefully I'll see you in class on Thursday. Otherwise, look forward to more videos. Please look into